This is Geometry, Lesson 9, Part 2, and it is our last lesson for the geometry unit. We're going to be doing Build Your Skills number 4, 5, and 6. Example 2 from the last lesson, right here, showed that regular hexagons fit perfectly around a common point or a central point. This means that it would be possible to tile a floor with tiles in the shape of regular hexagons. So if you had a floor that was all hexagons, okay? Now, what other regular polygons can be used to tile a floor? Give two possibilities and explain your answers. Well, the reason we were able to use a hexagon in our example was because we ended up with 3 full hexagons. So had we taken 360 and divided by an angle and got a decimal, then you can't do it. The number has to come out to a whole number of polygon. Okay, so I couldn't have had 3.5, right? It has to fit perfectly. So the requirement, this is part of our reasoning. When you divide by 360, the amount of polygons must be a whole amount. Okay, now the two easiest ones are number one, triangles. Okay, if you were to take 360 degrees and divide it by the interior angle of 60, it's going to take you 6 triangles. And that's going to look like a hexagon, right? Oop, mess up. Okay, and this is why it's got to be a regular polygon, because if you can't draw it, then it's not going to work. So there's your 6 triangles, and there's your central point. There's your 360, right? Each of them is 60 degrees, each chunk. Okay. The second one, the easiest tiling is squares. So and for squares, if we take 360 and divide it by the central angle of 90, or sorry, the central angle, the interior angle. And again, I'm just looking off the table and I also know these off the top of my head. You could end up with 4 squares is all you need, right? So if we were to draw this out, there we are. There's 4. And if I circle around, it's 4 times 90. Each of those is 90 degrees, four of them around a central point. So both of those, 6 and 4. Okay. All right. Um, you can try other ones and see if they work. Just remember, you got to end up with a whole amount after you divide by the interior angle. Okay. Number 5, octagonal. So 8-sided houses were popular in the 1850s. Here's one. And a number of historical octagonal houses exist in Canada and the United States. And one such building is the Captain George Scott House in Wiscasset, Maine, USA. So here it is. If the house is a regular octagon, what is the sum of the angles at the vertices where the exterior walls meet? Okay, so I'm going to try my best to draw an octagon here. They're a little tougher. And I bet you none of these that I draw are classified as regular polygons because my sides are not going to be equal. So what they're saying is there's one of the angles. What's the total? Okay. There's two ways to do this. We could go look at the table and get the interior angle and multiply by 8. Okay. So step 1. The interior angle is, for an octagon, you just look at your table, 135. So you go 8 times 135, and that should come out to 1080. Or you can do number 2, this other way here. You can do the total or sum equation. So the total, and I remember I'm just replacing the word sum with total. 180, 8 minus 2, and your total comes out to 1080. Okay. So there we go. There's the two different ways you can do this. Okay. B, if the front wall of the house is 10 feet wide, so one of the sides is 10 feet, what is the perimeter? Perimeter is distance around. Okay. So what is the distance around? So if there's 8 sides, perimeter equals 8 times 10 feet. I'll just rewrite that unit. So the perimeter equals 80 feet. Okay, and our last question. The floor of a gazebo, so it's just kind of an enclosure that you sit in. It's usually a hexagon. This is the floor. The floor is painted in a pattern that divides the hexagon into triangles. Draw the lines needed to divide the floor into 6 congruent triangles. So the easiest way to do this is to draw from corner to corner. And this is similar to our triangle around a common point that we did in example 4. Okay, like that. And then straight across. Okay. So if you do that, all these sides are equal. Okay, now it says, what are the interior angles of the triangles? And then classify the triangles by side length. Okay, so what I think we should do for this one is find the interior angle of the hexagon and divide by 2. Okay, so for the hexagon, it's going to come out to 120. So then the triangle would be 120 divided by 2. And you're going to notice something. That is the amount that is always necessary for an equilateral triangle. So we didn't even have to do any of this work here. If you knew that for a triangle, the interior angle is 60 for one that has sides that are all the same length, you could have just jumped to 60. Because when you have a hexagon with equal sides, when you do this, you create triangles with equal amount of sides. The triangles are equilateral. But I just wanted to show you in case you wanted to solve it like that. But as long as you explain, if you were to say 60 degrees because the triangle is an equilateral triangle, then that would be a fair explanation. Okay. And then our very last question. If the sides of the regular hexagon measure 3 meters, okay, so 3, which would mean these triangle sides are 3 because they're equilateral. What is the area of the floor? Okay, we don't have an equation for area of a hexagon. We're going to use the common one, base times height divided by 2 for triangles. Unfortunately for us, though, we don't have the height. So that is unknown. Okay, but we can find it. So that'll be our first step. And then what we'll do is find the area of the entire triangle and then multiply by 6. Okay. So step 1, I'm just going to show you half of it. So we got, if you split the bottom, it would come out to 1.5 because it's 3 across. Hypotenuse is 3. This is a right angle triangle now, and we don't know the height. The angle that we know is 60. Now you could use Pythagorean theorem here. You could use, or you could use sine, or you could use tan. It's up to you. There are multiple options here. So I'm going to go ahead and use sine. Sine 60 equals opposite over hypotenuse. I'm going to multiply by 3 on both sides. So you should know how I've gotten to here. Or just simply cross multiply. And then if you crunch this number and your calculator is in degree mode, you should end up with a decimal answer. Take 5. And we're going to carry that on to the next step. Oh, it's not in centimeters, it's in meters. Okay. So now we have the height. So actually, I'll just replace x with h. And you got the height. Now we can get the area. Of the entire thing. So, and along the bottom is 3. Okay, so area is base times height divided by 2. So the base is 3. The height is 2.59808 divided by 2. And we end up with 3.8971 centimeters squared. And then step 3 is total area. There's 6 triangles multiplied by 3.89712 centimeters squared. Remember not to square the number, that's just a unit. So the total area, it comes out to one decimal place, 23.4. And there we go. That is the end of lesson 9, part 2. You now have your assignment 5.3, and that is the end of unit 5, geometry.